Wow, you guys look surprised, shocked, amazed. I would be too if this is the first time I learned about those convergence theorems. But now, today, we're going to apply those to some examples. It's going to be really cool. Let's review the different convergence theorems, and everything is measurable. I'm just going to sort of do it in shorthand form. The monotone convergence theorem, I'll put Lebesgue monotone convergence theorem. How about that? Uh, this is that if you have f1 of x less than or equal to f2 of x, so on, everything also is almost everywhere because it only matters if it's almost everywhere. If you have that situation, also they're non-negative, then the limit of the integral over a of fk equals the integral of a of the limit of fk. Now, the Fatou lemma is that we have lim nth of the integral a of fk. Oh, and so for this one, the functions are non-negative, but nothing about the monotoneness where they increase like that. The lim nth of this, and there's some symbol I put in between here, the integral of a of the lim nth of fk. And I always have to think of my counterexample, and this is greater than equal to. Yeah, there's strict inequality in some cases. In fact, that's one of the questions. And then anyway, the Lebesgue Dominated Convergence Theorem, probably could just do dct for that. That's if you just have a sequence of functions and the limit as k goes to infinity of fk is equal to f, and then absolute value of a fk of x is less than g of x, and this is integrable, then the limit of the integral of fk over a equals the integral of a of the limit of fk. So those are the three integral convergence theorems in kind of shorthand form. All right, so let's do our first example. This is exercise 3.4.2. Give an example where there is no g in the dominated convergence theorem and the conclusion fails. So in other words, you do have the fact that a bunch of measurable functions have a limit, but there's no dominating function that is integrable, that is bigger than the value of the absolute value of the function for all x. And then it turns out that these two things are not equal. So let's see who can figure that one out. That's right, Lucas. You like those wandering bump functions, don't you? Good example. So here's an example. There are many, many other ones, but you could have a function fk of x equals, let's draw a picture of it first. Like this is k, and this is k plus 1, and this is 1. So let's see, if we wanted to write it in notation, it would be 1 if x is between k and k plus 1 and 0 otherwise. And then you get that, let's see, let's do each side of the equation. So the limit of the integral of a of fk would be the limit of just, it's always going to have area 1 underneath, which is just 1. And then, but then if you take the integral of a of the limit of fk as k goes to infinity, right? Well, the limit of this function as k goes to infinity at every x is just 0, because it eventually just, the bump goes past it. So this is actually the integral of a of 0, so that's equal to 0. So those two things are not equal, right? And the reason is we would need a g that is integrable and fk of x is, in absolute value is less than g of x for all x. And oh yeah, I guess I meant a for to be rn, sorry, to be r. Put that in there. Okay, for all x and r. And who can tell me what the g of x would have to be at a minimum? Yep, that's right, Shaylin. Good job. Right. And we would need, so look at that bump. G of x to equal 1. The function 1, but it's not integrable. Right? So that's a good example why you need that. All right, so the next exercise, so that tells you why you need that hypothesis. So the next exercise is 3.4.1, and that's give an example where there is strict inequality in Fatou's lemma. Okay, well, actually, the last example works because when the limit exists, the lim inf equals the limit. So you have a situation where this limit is 0, this is 1, and that would be 1 is greater than equal to 0, right? But I like when I'm dealing with lim inf to have an example where there is no limit of the function at all, but you always have a lim inf that exists for a bounded function. So let's see if we can come up with an example of a function. Another example of a function where it actually doesn't have a limit of fk of x. Now this is kind of tricky to think about. You might want to just stop and see if you can come up with an example. And but let's see if anybody can come up with one right off the top of your head. And I'll give you a hint. It looks sort of like this. Yes, that's right, Caleb. It's going to be going from 0 to 1. And that's going to be 1. Good. Yeah, I'm kind of trying to force the lim inf to be 0, but there'll be no limit if this thing wanders around a lot. Yeah. Yeah, that's a good idea. Put like 1 over n there, then yeah, but it actually, that would only give us a sequence of points close to there. It would still have an actual limit, I think. Yeah. Think rational numbers. All right, yeah, Peter, good idea. So I'm going to let Q1, let's say we enumerate, we know that the rational numbers are countable, so if we intersect them with the 0, 1, let's make it open interval. So we still have the endpoints. Let's say we list them like that, and this be QK. And so if we actually draw that picture, then notice that the integral of fk of x, no matter where we put that, the answer is going to be 1/2, right? Sum of two triangles, 1/2 times base times height, right? Height's 1, and whatever this is, the two bases add up to 1. So it's the same as if we had one triangle going like that. Okay. Good. So that's true, but the lim_inf of fk of x is, as k goes to infinity. So remember, that means you take the infimum over all possible values large enough, where the k is large enough for each x. But if you think about it, the q's are going to be dancing all over the place forever. So it's actually equal to 0 in the middle. And then 1 if x is in. So the lim_inf of the function is just, that's the lim_inf. And then if we take the integral of, well, let's see, I stated it the other way. Lim_inf as k goes to infinity of the integral of fk over 0 to 1. This equals, it's always 1/2, which is greater than the integral of 0 to 1 of lim_inf of fk, which is, the integral is just going to be 0, nowhere, right? So that's an example where another example where the Fatou lemma has strict inequality. Right. Okay. You guys are doing great on this. All right, so now I wanted to show you a really fun example of an application of the dominated convergence theorem. And there are many examples like this. So so I want you to compute the limit as k goes to infinity of the integral over r of e to the minus x squared over k times cosine of x over k all over x squared plus 1 dx. Now, of course, one way to do this would be compute that integral. It's a function of k. All the x's will be gone, and then you just take the limit as k goes to infinity. However, good luck computing that integral. It's going to be pretty rough. Yeah, Peter, I know you like pain, but yeah, not today. All right. So let's actually see if we can get this to satisfy. So this right here will be our fk of x. And yes, it's bouncing all over the place. It's not non-negative. That's sometimes negative, whatever. However, notice that absolute value of fk of x, I can bound it by something integrable. So this equals the absolute value of e to the minus x squared over k cosine of x over k over x squared plus 1. Okay. So what can I bound the e to the minus x squared over k by? That's right, then. Go frogs! Yeah! Yeah! Oh, sorry. need to control myself. Right, so I can put a 1 there. That's, all right, because that's, yeah, all right. What about the absolute value of cosine? What's that always between? Right, Shaylin? Right. Also, in absolute value, it's always less than or equal to 1, or x squared plus 1. And what's great about this is we know that 1 over x squared is in L of R. It's the Lebesgue interval. It gives you arctan, and it has a limit with the improper integral. We'll see that in a second. So therefore, this guy, these are all measurable functions, all good. All the things that you know, they're all continuous, for instance. These are continuous functions, so measurable. So we have satisfied the Lebesgue Dominated Convergence Theorem. So we have that this guy equals the integral from R of limit as k goes to infinity. So that's what all these things are about, is interchanging the integral and the limit sign. And we can go e to the minus x squared over k cosine x over k over x squared plus 1 dx. And then we take the limit of k. So as k goes to infinity for each x, as k goes to infinity, that goes to the 0. So this is integral of e to the 0. And then, yeah, we're looking at it for fixed k. As k goes to infinity, that goes to 0. So that goes to 1. Divided by x squared plus 1 dx equals integral over r of 1 over x squared plus 1 dx. And we know from calculus, we can compute this, because arctan is the derivative of that is that. And we go between negative b and b. And tangent goes to infinity when you get to pi over 4, and negative infinity when you get to negative pi over 4. So it's pi over 4 is that limit minus negative pi over 4. All right, I mean, tangent looks like this. Oh, wait, pi over 2, right? Is that where it flows up? Yeah, pi over 2. Negative pi over 2. Boy, I'm glad I drew that picture. That's tangent. And then arctangent, you flip it the other way. So this one has an asymptote of pi over 2 and negative pi over 2. Oops. And fix that. And so the answer is pi. Wow, so that's what that limit is. So the Lebesgue Dominated Convergence Theorem allowed us to compute that. But remember, you need that g to be able to do that. Otherwise, you're not going to be able to compute that. So good job, guys. See you next time.